Okay, so we're going to talk about related rates today. And so in calculus, what we do sometimes is we take the derivative of different functions, and sometimes we'll have two different things changing, or two rates of change within one problem. So first, let's kind of revisit how we take derivatives and how they relate to rates of change. Suppose there's a particle that's moving on a curve C in a plane such that x and y are differentiable, and d is the distance from the origin to P. How would we go about finding an equation that relates the difference in distance with regards to x and y? So we have three things that change. The distance changes, the x changes, and the y changes with respect to time. And so this is a typical related rates type approach. And basically what we're going to do is we're going to differentiate almost implicitly, except we don't necessarily always solve for a particular derivative. So let's consider the distance. Well, the distance formula is x sub 2 minus x sub 1 squared plus y sub 2 minus y sub 1 squared. But we said that our initial point, x sub 1, y sub 1, was the origin, which is 0. So when you plug in the zeros, when you subtract 0, you're really left with x squared plus y squared. Okay? And so the distance, the formula for distance from the origin in this particular case is just the square root of x squared plus y squared. And that's based on the old algebraic distance formula. So the first step is always going to be to write out a formula and then differentiate. So now that I have an equation, I'm going to differentiate with respect to time. Remember that the square root of x squared is actually the same as raising everything under the radical to the 1/2 power. So we could think of it as the quantity x squared plus y squared raised to the 1/2. That makes taking the differentiable, or taking the derivative easier, because then I can apply the power rule. Toss the 1/2 to the front, x squared plus y squared raised to the negative 1/2, and then we have to tack on the derivative using the chain rule. So x squared is going to become 2x dx dt, and then y squared is going to become 2y dy dt. And that's it. We were only asked to write an equation, so now we have an equation. But in these related rates problems, what they're going to do is they're going to give us what dx dt is, or dy dt, or sometimes dd dt. And then we plug it into the formula. So sometimes they'll ask for dx dt, or maybe they'll ask for dy dt. They're going to give us a whole bunch of stuff or information, and then we plug it into the formula, and we'll either get an answer or an equation with one or possibly two variables. Remember that dx dt and dy dt are the rates of change for x and the rates of change for y. So when we talk about derivatives, remember they're measuring the rate of change. So dx dt and dy dt are rates of change of x, rates of change of y, or dd dt is the rates of change of distance. So example number 1 out of the textbook gives us or asks us the question, and I won't write it all down, I'll just state it out loud. It says, assume that the radius of a sphere is a differentiable function of time. Let's let v be the variable of the sphere. Find the equation that relates dv dt to dr dt. And so we start with the regular formula, the formula for the volume of the sphere, which is the volume is equal to 4/3 pi times r cubed. So we always start off with a general formula or equation, and then we take the derivative with respect to time, or t in this case. So once I have the formula written down, I'm just going to take d dt of the whole thing and then go from there. And then the second part says, assume that the radius and height of a cone are differentiable functions, and we're going to repeat the process. So first let's do the sphere. So the change in the volume with respect to time is the derivative of this. Now 4/3 pi is a constant, so we can leave that alone. Then we take the derivative of r, But remember that once we take the derivative of r, we have to tack on dr dt. In other words, we're taking the derivative of r with respect to t. So then our rate of change in volume actually becomes 4 times pi r squared dr dt. So there's a relationship between the change in radius and the change in volume, which kind of makes common sense. But now we have a mathematical formula that'll help us make those predictions. So as the radius of the sphere changes, so will the volume of the sphere. And this is the mathematical relationship between the change in the radius and the change in the volume. Okay? Now let's do the cone. So again, we're going to start off with a regular formula for the volume of a cone, which is pi over 3 r squared times the height of the cone. Then we're going to take the derivative with respect to t. So we'll end up with dv dt, toss our constant out front, pi over 3. And now, because we're dealing with r squared times h, remember that's just the product rule. uv prime we use the product rule, and Mr. Adams is getting a little sloppy with his notation, but that's okay. I'm trying to do this in a hurry. So we list r squared is u prime would be 2r times the derivative, and then v is h, and then the derivative of that would be 1 times, and then we have to tack on dh dt and or dr dt. And so remember the product rule for uv prime is going to be uv prime plus vu prime. So now we plug and chug. So I've got r squared dh dt plus 2r times h, and then I'm going to tack that dr dt on the back end. And so that's our formula or equation that relates the volume of a cone. Now, it makes sense that the change in volume of the cone would be related to the change in the height and the change in the radius. So if one changes, both changes, or none of them change with regards to the height and the radius, then obviously that'll have an impact on the rate of change of the volume. And so dv dt is the change in volume, dh dt is the change in height, and dr dt is the change in radius. And we can assign numerical values to those. Oh, the bell rang. So we can assign some numerical values to those and plug those in and actually determine rates of change for volume, the height, or the radius of the cone based on whatever information that we're given. So in example number 2, we'll do just that. So example number 2 says a hot air balloon is rising straight up from a level field and is tracked by a ranger that is about 500 feet away from the liftoff point at the moment of the ranger's elevation of the balloon. So the instant that he sees the balloon, the angle of elevation is about pi over 4. So that's our initial theta or angle, and it increases at a rate of 0.14 radians per minute. That is a change in theta, or d theta dt, which is going to be 0.14 radians per minute. Keep that in mind, right? That's our rate of change. That's how much theta changes with respect to time. So we put 0.14 radians, which is theta, over time, which is 1 minute. Sometimes we need to do a conversion on the time, but they didn't give us any specifics. We are also asked to find dh dt. In other words, how quickly does the height of the balloon change? What's the rate of change of the balloon? And so that's our task. So the first thing we need to do is write our general equation. Well, I have a right angle triangle. I have the opposite and the adjacent and theta. And so SOHCAHTOA reminds me that tangent of theta is equal to the opposite over the adjacent. So now I plug in the values that I know. Tangent of theta is equal to the height over 500, which is the length of the adjacent. I'm interested in the height, or the change in height, so what I'm going to do is mathematically solve this equation for h and then take the derivative with respect to t. By multiplying both sides by 500, I get 500 tangent of theta is equal to h. Now I just need to take the derivative with respect to t. 500 is a constant, we toss that out front. The derivative of tangent of theta is going to be secant squared of theta, and that's equal to dh dt. Oh, I got to remember to tack on that d theta dt. I almost forgot. Whenever we take the derivative of theta, we got to tack that on. So now I have an equation that's written with respect to dh dt. So now I just got to plug in the numbers and I'll get a numerical value for the rate of change of height. So 500 secant squared of pi over 4 times 0.14. And I could list the radians per minute, but I'm going to omit that. In fact, let me erase that real quick because we'll talk more about unit conversions in a second. For right now, I just want you to process how to plug the numbers in. So let me pull that out. If you plug that in the calculator, 500 times the secant of pi over 4 squared times 0.14, you get 140 units per minute. And that's the rate of change for the height in time. So if they were to give us a measurement, an initial measurement in feet, it would be 140 feet. The textbook isn't very clear, but it's a unit per minute, and that's how you would go. I believe that it would be feet because I think, if I remember correctly, the original measurement was 500 feet. So it should be 140 feet per minute. Okay? And it didn't specify if they wanted that converted to seconds or not, so we could leave it as per minutes. Lastly, we have example number 3. And example number 3 is there's a police officer that's a little bit a ways from intersection, and then a speeding car comes by and goes past the police officer. And what we're asked to do is we're going to let x be the distance of the speeding car from the intersection. We'll let y be the distance of the police officer from the intersection, and we'll let z be the distance between the car and the police officer. The distances x and z are increasing, but y is decreasing, so dy dt is negative. So I'm going to draw a little picture here to kind of set things up and wrap my mind around it. The police cruiser is approaching the intersection from the north and is chasing another car who is moving straight east. The cruiser is operating at is actually located 0.6 miles north of the intersection, and the speeding car is 0.8 miles east. And then if our question is if the cruiser is moving at 60 miles per hour, the instant of measurement, what is the speed of the car? And then one other thing of information is that the police determine with radar that the distance between them and the car is increasing at 20 meters per second. So we have a lot of changes, all right? The police officer is approaching the intersection at 60 miles per hour. The rate of change between the police officer and the car is increasing at 20 meters per second. So there we have our dy dt, which is negative because that value is decreasing or approaching 0, and then dz dt, which is the increase in speed between the police officer and the car. The relationship between x, y, and z is the Pythagorean Theorem, so I write the formula x squared plus y squared equals z squared, and then I take the derivative with respect to time. Now, what we're trying to figure out is what is the rate of change of the car, okay? So I have a bunch of stuff listed up here after I take my derivative, and what I want to do is start simplifying. So everything after I took the derivative had a coefficient of 2. I multiply the whole equation by 1/2 and get rid of the 2's. Next, I'm going to solve algebraically for dx dt because that's what I want to find. When I do that, I get z dz dt minus y dy dt all over x, because dx dt is what we're solving for. And then I got to check and see if I have a bunch of information that I can plug in and some numbers I can plug in for these variables. So as I read the example earlier, it said the police cruiser is approaching a right angle intersection from the north, chasing a speeding car that has turned the corner and is now moving straight east. When the cruiser is 0.6 miles north of the intersection, the speeding car, is 0.8 miles to the east. The police determine with the radar that the distance between them and the car is increasing by 20 miles per hour. The cruiser is moving at 60 miles per hour at the instant of measurement. So my y value is 0.6, my x value is 0.8, but I need to calculate the distance z. That's the Pythagorean theorem. So it's, or the distance formula, however you want to look at it. But z is the hypotenuse of this right angle triangle. So I'm going to take the square root of 0.8 squared plus 0.6 squared. And when I do that, I get 1. So now I have a numerical value that I can plug in for each variable. When I plug all those numbers in, I get that the rate of change, dx dt, in other words, the change in distance of the car is going to be 1 times 20 minus 0.6 times negative 60, all divided by 0.8, which gives me 70 miles per hour. So that car was going 70 miles per hour. He was going pretty fast. And that's pretty much it for related rates of change.